So what we're going to have a look at here is parallel resistance. We've got two circuits, one with 2 resistors and one with 3 resistors. To work out the total resistance, it's basically R1 times R2 over R1 plus R2. Or you can use this formula here, which is 1 over R1 plus 1 over R2. Or what you can do, if they're the same value, as in here they're 1k each, so you've got a 1k and a 1k, you can actually just take 1k ohms and divide it by 2. So it's just the number of resistors in the circuit. But as I point out here, it only works if they're the same value. If you look at a combination of 3 resistors in parallel, the only formula that you can use is this one here, which is total resistance equals 1 over R1 plus 1 over R2 plus 1 over R3. Or if they're the same value, like the top circuit, you can take the value of one of the resistors, like in this case 3.3 k ohms, and divide it by the numbers of resistors in the circuit. So in this case we've got 3 resistors in the circuit. They're all 3.3k, so we divide it by 3, and like I've outlined here again, that only works if they're the same value in that parallel combination. So if we're looking for the total resistance and we use the first formula, you can see here that we've got 1k ohms times 1k ohms divided by 1k plus 1k. That basically gives you 1,000,000 ohms divided by 2,000 ohms, and if you work that out you end up with 500 ohms. The same happens in this situation but done differently. So what we're doing here is 1 over 1k plus 1 over 1k again. If you work that bottom bit out, the denominator, you basically end up with 1 times 10 to the negative 3 plus 1 times 10 to the negative 3. And then you end up adding these two together, you end up with 1 over 2 times 10 to the negative 3, and if you work that out you end up with 500 ohms. And the last one, and like I said, only if they're the same value, like both resistors are the same value in the parallel circuit, then it's just 1k divided by 2 and you end up with 500 ohms. So what we've got here are 2 resistors in parallel. So basically you've got this common, this common row up here, and we have another common row down the bottom. I just had to join up a few things here to make it all one row. And we've got our 2 resistors there, they're both 1k. And what we'd expect to find, seeing that they're in parallel, is what we worked out on the board. So if I go across these resistors, you can see here that we're getting something very close to 500 ohms, which is what we're getting there. It doesn't matter which ones I go across. If I go across the other ones, I'm still going to get this, the same type of value, right? So that principally proves that 2 1k resistors in parallel, if measured, will give you 500 ohms. So what we're going to have a look at now are 3 resistors in parallel. As you can see, we've got 1, 2 and 3. The value of each of the resistors is 3.3k ohms. And to calculate the total resistance of this circuit, we'll have to use this formula here. So you've got RT, which is total resistance, equals 1 over R1 plus 1 over R2 plus 1 over R3. That's just broken down into here. And if you calculate this out, you get 1 over 303 times 10 to the negative 6 plus 303 times 10 to the negative 6 plus 303 times 10 to the negative 6. And then if you calculate that out, you get 1 over 909.1 times 10 to the negative 6. And there's a bit of rounding in here and up there, so just be aware of that. Once you do this calculation, you end up with 1.1k ohms, or what's 1,100 ohms, and that's 1/3 of one of the values of the resistor. Or you can do it this way, because these resistors are all the same value, you just pick a resistor, so 3.3k ohms, and you count up the number of resistors in the circuit. We've got 3, so you divide it by 3, and as you can see here, 3.3 k ohms divided by 3 gives you 1.1 k ohms or 1100 ohms. So just to prove what we had up on the board and that the calculations do work, we got 3.3 k ohms resistors in parallel, and what we'll do now is just measure the overall resistance, or the total resistance of this circuit. You get pretty close to 1.1 k ohms, keeping in mind that you've got tolerances that you deal with. Now it doesn't matter which resistor you measure across, you're going to end up with the same value, as you can see, anywhere in that parallel right combination. Now the reason we're getting slightly different reading is just the tolerances within the resistors. So what we're going to have a look at now is a situation where you have a low value resistance in parallel with a much larger value resistance. So the methods that we can use now is either write the total resistance using the product over the sum, or we can use the total resistance using 1 over R1 plus 1 over R2. As you can see here, we've gone through the steps, so we multiplied them on the top, we've added them on the bottom. You come out with these super large numbers right as you get here. So we're going to divide the top by the bottom, and we end up with a value of 219.8 ohms. Now I'll talk about that in a minute. If you do it this way, you've got 1 over R1 plus 1 over R2, which is your 220 ohms, 220 k ohms. You do the maths there, you can see here we've got 4.545, that's actually recurring, that's what that bar means, times 10 to the negative 3, and then you've got the kind of the same value again, times 10 to the negative 6. If you then invert, you add these up and then put them down here and then invert it, you end up with 219.8 ohms, so we get the same value. But the interesting point is that in a parallel combination, the total resistance value of that combination will always be close to or less than the lowest value resistor. And that's how you know that your calculations are close to where they should be, or are where they should be. Now we can prove that on the test board here. We've got 220 ohms here, and we've got 220 k ohms here. Now we should see a value on or close to 220 ohms. And again, it doesn't really matter which resistor you measure it from. These things are quite slippery. So you can see here we've got 220 ohms, right, is the reading we're getting here. And if I go over to the larger resistor over here, you can see that we still get the same value of 220 ohms. Now you are getting a slight variation here, because if I actually measure out my leads, you can see I'm getting about 0.4 ohms in my lead, so the value should be slightly under the lowest resistor. But what's happening here is that you've got your lead resistance you're playing with, and you also got the tolerance values of your resistors, and again these are 5% tolerance values, so they can vary 5% above or below their marked value. So now we'll look at 3 resistors in parallel, and these are all different numbers. You've got 220 ohms for R1, 68k for R2, and 470k for R3. Now if you're working out the total resistance, you'd have to use this method here, 1 over R1 plus 1 over R2 plus 1 over R3. If you put the figures in, you've got 270, 68, 470, you end up with these numbers. You can see here you've got 4.545 times 10 to the negative 3, and then you've got plus 14.71 times 10 to the negative 6, and then you've got 2.13 times 10 to the negative 6. Work out the bottom row again by adding them all up, and you end up with 1 over 4.562 times 10 to the negative 3, and keeping in mind that there's a bit of rounding that's going on in this section here. And we should end up something close to this low value, and again we achieved that. We've got 219.21 ohms. So we've done that on the board here. We've got the three resistors in parallel. We've got 220 ohms, you've got 68k and 470k. And if we do our resistance measurement, find out what our total resistance is, you should end up something close to 220 ohms. So you can see there that we've got 220 exactly. Doesn't matter which ones you go over, you're going to end up with the same value, because it should always, in a parallel circuit, it should always be just slightly less than the lowest value. Now, keeping in mind, again, as I mentioned before, we've got the test lead resistance to take into account, but you've also got the tolerance values of these resistors, and again, they're all 5%. So you've got 5% above and below, which they can read and still be within tolerance as far as their noted values are. So I think that basically proves the math behind parallel resistance, and the fact that it doesn't matter, if you had four resistors or 5 or 6 in parallel, it's always going to be equal to or close to the lowest resistance.